Assalamualaikum warahmatullahi wabarakatuh. A very good day to all of you. So for part number 3, we will start with specific humidity omega and also relative humidity psi determination. So now we want to learn how we want to determine the value of in terms of I call the value of specific humidity omega and also relative humidity psi. Okay, so we want to know the simple way to determine the humidity value based on the measurable quantities such as pressure and also the temperature. Okay, so we want to know the method by measuring pressure and also temperature. We can determine the value of humidity, including the specific humidity and also the relative humidity. First method, we can determine the humidity value by referring to the dew point temperature. So if we know the value of dew point temperature, from the value of dew point temperature we can determine the partial pressure of water vapor, PV. And by using what I call the formula, the basic formula for relative humidity psi, where psi equal to PV divided by PG. So we can substitute PV value, and also the PG value we can determine from the what I call the saturated water table, where PG equal to P saturated at specific temperature. So we can determine the value of relative humidity. And then we also can determine the value of omega, specific humidity, by using this formula where omega equals 0.622 PV divided by total pressure minus PV. Okay, we just substitute the value of PV, and the total pressure we already know because the value is equal to 1 atm. Although this method is simple, but it's not practical because we don't have what I call the specific device that can measure directly the dew point temperature. Okay, so this method is simple but not practical because we cannot measure directly the value of dew point temperature by using a thermometer. There is no typical thermometer that can measure dew point temperature directly. And the second approach is by using the adiabatic saturation process. This schematic diagram shows the adiabatic saturation process device where we have a channel with liquid water pool inside the channel. So we have inlet at state number 1 and so outlets at state number 2. So at the inlet we have the condition for unsaturated air, so the condition where we want to determine the value of omega 1 and also the value of relative humidity psi 1. And the outlet condition, so normally the condition of state number 2 is known, where we need to make sure that the condition at the outlet must be at saturated air, where the value of psi 2 or relative humidity at the outlet is already determined, where the value must be 100%. Okay, the water level inside the adiabatic saturation process device must be constant. Okay, so if we look to the TS diagram, the adiabatic saturation temperature actually is not equal to the dew point temperature, because the adiabatic saturation temperature is based on the value of the atmospheric pressure. Okay, so the dew point temperature based on the partial pressure of water vapor pressure. Okay, so for this case, for this process, omega 1, psi 1, relative humidity 1 are unknown, so we want to determine by using this process. So later on we will discuss detail about the adiabatic saturation process. Specific humidity omega and also relative humidity psi determination based on the adiabatic saturation process. So now I will explain detail about the adiabatic saturation process in order to determine the value of humidity. So we'll use for the adiabatic saturation process, we'll use long insulated channel with a pool of water. So this is the simplified, the adiabatic saturation process device, where we have long insulated channel. So we need to make sure that this device is long enough in order to make sure that the outlet condition will be at saturated air condition. So inside the channel, we will have a pool of water, where we have additional liquid water piping line in order to make sure to maintain the level of liquid water inside the channel. So the temperature of the liquid water will be at T2. Okay, so we have first condition at the inlet condition of the channel, state number 1, and the condition of the air is unsaturated air. So the air will enter the inlet of the channel, and the red dot represent the dry air, and the blue dot represent the water vapor. Okay, so we can see that the amount of dry air is greater than amount of water vapor. So we consider the state number 1 condition as unsaturated air condition. So in terms of parameter that involved at the state number 1 are T1, temperature 1, omega 1, relative specific humidity, psi 1, relative humidity. We have mass flow rate for water vapor, mv1 dot, mass flow rate for dry air, ma1 dot. So the air flow through the channel. So during the process, the airflow will transfer heat to the liquid water, and the evaporation will occur, where we will have additional water vapor due to evaporation into the air. So the amount of water vapor in the air will increase due to this evaporation process. So in terms of new parameter involved during evaporation, we will have mf dot, the mass flow rate for the additional water vapor into the air. So because the channel is long enough, in order to make sure that the condition at state number 2 at the outlet of the channel is saturated air, so we can see that the increase of water vapor mass at the outlet of the channel. So we consider this condition as saturated air. So at the outlet of the channel, in terms of parameter, we have mv2 dot, represent the mass flow rate of the water vapor, ma2 dot, mass flow rate of dry air at the outlet. So because the condition is saturated air, so the relative humidity psi 2 is equal to 100%. So we also have the value for omega 2, specific humidity at the outlet, and also the T2, the temperature of the air at the outlet. Okay, so the T2 value, T2 temperature, the temperature at the outlet, is considered as the adiabatic saturation temperature, which is also equal to TAS, adiabatic saturation temperature. So the purpose of this explanation, actually we want to determine the equation for omega 1, the specific humidity at the inlet of the channel, by using adiabatic saturation process. Okay, so if you consider mass balance equation for dry air, because the amount of dry is constant, so ma1 dot will be equal to ma2 dot equal to ma dot, where the value is constant for dry air. For water vapor, because during the process involved is evaporation process, where we have additional amount of water vapor due to the evaporation. So in terms of mass balance equation, so we will have mv1 dot plus mf dot equal to mv2 dot. So mass flow rate of water vapor at the inlet plus mass of water vapor, additional water vapor during the evaporation into the air, will be equal to mass of water vapor, mass flow rate of water vapor at the outlet. So because we know that the formula for omega equal to mv divided by ma, so we just rearrange the equation, substitute into the equation of mass balance equation for mass flow rate of water vapor. So we will get ma dot multiplied by omega 1 plus mf dot equal to ma dot multiplied by omega 2. So for evaporation process, if we rearrange the equation, mass balance equation, this what I call the second mass balance equation for water vapor, so we will get the formula for additional mass flow rate for the water vapor during the evaporation process, where mf dot equal to ma dot multiplied by omega 2 minus omega 1. Okay, so these are the equations that that involved during the what I call the adiabatic saturation process. Okay, now we still consider the long insulated channel with a pool of water in order to discuss about the adiabatic saturation process. So in this slide, we will derive the equation for omega for the specific humidity. Okay, in order to determine the humidity value for the air. Okay, by using the adiabatic saturation process concept. Okay, so we look at the same schematic diagram as previous slide. So we have the inlet condition, unsaturated air, and the outlet condition as saturated air condition. So for the channel, we have the what I call the additional pipeline for makeup water. Okay, where we want to make sure that the constant what I call level of the liquid water inside the channel. So in terms of rate of makeup water must be equal to rate of evaporation in order to maintain the water level inside the channel. Okay, so for this process, we can consider the device as the steady flow device. So if we implement energy balance equation, Q dot during the evaporation will be 0 because the heat transfer occur within the boundary condition. Okay, so that's why Q dot equal to 0, and there will be no work in and also work out during this adiabatic saturation process. That's why W dot also equal to 0. Okay, so we know that the energy balance equation will be E in dot minus E out dot. So implement the energy balance equation to the adiabatic saturation process. So we will get MA dot multiplied by H1 plus MF dot multiplied by HF2 equal to MA dot multiplied by H2. So the energy equation only will involve with the E mass in and also E mass out. Okay, so now if we replace the value of MF dot with the equation that we already derived before, so you will get MA dot multiplied by H1 plus MA dot multiplied by omega 2 minus omega 1 multiplied by HF2 equal to MA dot multiplied by H2. Okay, so we just replace the MF dot with MF dot equal to MA dot multiplied by omega 2 minus omega 1. Okay, so if we divide the equation with MA dot, so we will get H1 enthalpy 1 at the inlet plus omega 2 minus omega 1 multiplied by HF2 equal to H2. As we know that the general equation for enthalpy, H equal to HA plus omega Hg, and HA also equal to CPT. Okay, same as for the H2. So substitute into the equation, so we get CPT1 plus omega 1 Hg1 plus omega 2 minus omega 1 multiplied by HF2 equal to CPT2 plus omega 2 Hg2. Okay, and then if we rearrange the equation, we can derive the equation for omega 1, where omega 1 equal to Cp T2 minus T1 plus omega 2 HFG2 divided by Hg1 minus HF2. Okay, so the value of HF, HFG, Hg we can determine from the saturated water table based on the specific temperature. And also we will get the equation for omega 2, where omega 2 equal to 0.622 Pg2 divided by P2 minus Pg2. So Pg equal to saturated pressure at temperature of T2, and P2 equal to P1 equal to atmospheric pressure. Okay, so the value of omega 2 is the formula for saturated air. So that's why we have inside the equation we have the pressure of P saturated, Pg. Okay, so for this formula we do not know what is the value of T1 and also T2 are referred to. So later on we will try to identify what is the value for what is the temperature for T2 and also T1. So if we can identify these two temperature, we can determine the value of omega 1 easily. Okay, for P2, P2 is equal to P1 equal to the atmospheric pressure. Okay, so in order to determine the specific humidity and also relative humidity, the device that can be used we call the SLING psychrometer. Okay, as we know, for the adiabatic process, the device for the adiabatic saturation process we call the adiabatic saturator. Okay, so in order to to make sure that the condition at the outlet is saturated air condition, so the adiabatic saturator, the adiabatic saturator can be a long insulated channel, or we can use a channel with a spray mechanism in order to make sure that the saturation air condition at the exit of the device, of the saturator. So because probably if we look at the adiabatic saturator, so the size and also the length of the device might be too long and also too big, so not practical to make this kind of of this device as the practical device for measure the humidity, specific humidity and also relative humidity. So the practical approach in order to determine the humidity, we will use a device that we call SLING psychrometer. Okay, so this SLING psychrometer actually use the same concept of adiabatic saturation process, where we will use the ordinary thermometer and we will put at the thermometer bulb a wet cotton wick, and we have the container with liquid water, and we allow the device so we provide the airflow to the wet cotton wick in order to promote the evaporation. Okay, so this kind of thermometer will measure the wet bulb temperature. So this kind of thermometer we call the wet bulb thermometer. So this is the basic principle for the SLING psychrometer. Okay, so this thermometer will measure the wet bulb temperature, and the device of SLING psychrometer as shown in the figure, where the device consists of two types of thermometer. We have dry bulb thermometer, which is referred to the typical or normal thermometer, and the second one we will have the wet bulb thermometer, where we have the bulb at the thermometer bulb we will have what I call the wet cotton wick. the wet carton wick. Okay, so in order to provide the airflow, so we need to rotate the SLING psychrometer, okay, as shown in the photo. So we will have the two type of temperature from this device. So we have wet bulb temperature and also dry bulb temperature. So by rotate the SLING psychrometer, we will provide airflow to the device. Okay, for SLING psychrometer, so this device we will use to determine the humidity for the air. Okay, in terms of how to use this SLING psychrometer, we need to rotate the SLING psychrometer in order to obtain, in order to provide the airflow, and then we will obtain the two type of temperature, which is the dry bulb temperature and also the wet bulb temperature. So in terms of principle of the SLING psychrometer, the principle is similar with the adiabatic saturation process principle. Okay, so the figure shows the adiabatic saturation process that we already discussed before. So if you compare with the wet bulb thermometer, so for the wet bulb thermometer we have airflow, and the air we consider as unsaturated air, and the air will flow through the wet carton wick. So we have the temperature for unsaturated air, the air, and due to the airflow, the heat transfer process will occur. Okay, so the heat will transfer to the wet carton wick, and the evaporation process will occur. So the amount of water vapor inside the air will increase, and water evaporate, and we have Q gain and also Q loss, heat gain and also heat loss through the process. And we have, in terms of water temperature, the temperature will reduce due to the evaporation process. Okay, so the temperature, so for the process we will have temperature difference. So the temperature difference between air temperature and also the water temperature. So during the process, based on energy balance equation, the value of Q gain, heat gain, will be equal to the value of Q loss, heat loss. Okay, so from this meter, the thermometer will measure the wet bulb temperature that represented by TWB. Okay, so basically the value of wet bulb temperature is not equal to the adiabatic saturation temperature. As we can see in the TS diagram, so the wet bulb temperature is not equal to the adiabatic saturation temperature. Okay, so the adiabatic saturation temperature actually is the saturated temperature at the atmospheric pressure. However, for air vapor mixture in atmospheric pressure application, we can assume that the wet bulb temperature is equal to the adiabatic saturation temperature, where the value is referred to the value of T2, the temperature at the outlet of the adiabatic saturation process device. So if we look at the equation that we derive from the adiabatic saturation process, we have omega equal to Cp multiplied by T2 minus T1 plus omega 2 HFG2 divided by Hg1 minus HF2. So the numbering actually based on the inlet and also outlet condition of the adiabatic saturation process device, where number 1 represent the inlet condition, number 2 is represent the outlet condition. And also we have the formula for omega 2, where omega 2 equal to 0.622 Pg2 divided by P2 minus Pg2, where Pg stand for P saturated at specific temperature, P saturated at temperature number 2. and P2 equal to P1 equal to atmospheric pressure for the air. So now T1 actually refer to the dry bulk temperature, TDB, and T2 represent the value of wet bulk temperature, TWB. So by using the SLING psychrometer, we can determine the value of T2 and also T1. Okay, so T2 represent wet bulk temperature, T1 represent dry bulk temperature. Okay, the rest, for example, HFG, HG, and also HF. HFG we can determine from the saturated water table based on T2 temperature or wet bulk temperature. HG we can determine also from saturated water table based on T1, which is referred to the dry bulk temperature. And the last one, HF, refer to the saturated water table based on T2 temperature or wet bulk temperature. So from this value we can determine the value of omega 1, okay, the specific humidity, and the value of omega 2 in equation of omega 1 we can determine from the second equation for omega, where omega 2 equal to 0.622 Pg2 divided by P2 minus Pg2. Okay, so by using this by using the SLING psychrometer device, we can determine the value of wet bulk temperature and also dry bulk temperature, and then we can determine the value of specific humidity. Okay, so from the SLING psychrometer we can determine two types of temperature, wet bulk temperature and also dry bulk temperature. Okay, now we try to generalize the equations for the omega that we obtain from the adiabatic saturation process, and now we want to generalize the equation based on the SLING psychrometer. Okay, as you know, from the SLING psychrometer we can determine the value of wet bulk temperature and also the dry bulk temperature. Okay, so wet bulk temperature actually same as the value of T2 for the adiabatic saturation process, and value of dry bulk temperature TDB is also the dry bulk temperature TDB is equal to the temperature for T1 for the adiabatic saturation process. So now in the equation, instead of we use T2 and also T1, we will use TWB and also TDB. Okay, so based on the temperature value they obtained from the psychrometer. So for the specific humidity equation omega that we obtain from the adiabatic saturation process, so we will use this equation where omega equal to Cp multiplied by TWB, wet bulk temperature, minus TDB, dry bulk temperature, plus specific humidity omega set represent the specific humidity at saturated air condition, multiplied by HFG at wet bulk temperature. So we can determine the what I call the value of HFG based on the saturated water table by referring to the wet bulk temperature, and divide by Hg at dry bulk temperature minus HF at wet bulk temperature. So this is the generalized equation for omega based on the temperature that obtained from SLING psychrometer. And the value of W set or specific humidity during the saturated air will be equal to 0.622 multiplied by Pg at TWB divided by P total minus Pg at TWB. Okay, in terms of relative humidity psi, so we can use the formula of psi or relative humidity, where psi equal to omega Pg at TWB divided by 0.622 plus omega multiplied by Pg at TDB, Pg at dry bulk temperature. Okay, so from this equation we can determine the humidity value for specific humidity and also for the relative humidity. Okay, example 6.3, the dry and the wet bulb temperatures of atmospheric air at 1 atm, which is also equal to 101.325 kilopascal, pressure are measured with a SLING psychrometer and determined to be 25 degrees Celsius and also 15 degrees Celsius respectively, which means the value of dry bulb temperature is equal to 25 degrees Celsius and the wet bulb temperature equal to 15 degrees Celsius. Determine A, the specific humidity, omega, B, the relative humidity, psi, and also the enthalpy of the air, H. Okay, question A, first we need to determine the specific humidity, omega, for the air. So in terms of data given, dry bulb temperature equal to 25 degrees Celsius, wet bulb temperature equal to 15 degrees Celsius, P total equal to 1 atm equal to 101.325 kilopascal, and the value of Cp for the air equal to 1.005 kilojoule per kg Kelvin. Okay, from the saturated water table based on temperature, so for the wet bulb temperature, we can determine the P saturated at a wet bulb temperature where the value is equal to 1.7051 kilopascal, and for the at the dry bulb temperature of 25, we can obtain the P saturated at dry bulb temperature, which is equal to 3.169 kilopascal. So now we get the value for P saturated at 15 degrees Celsius equal to Pg at 15 degrees Celsius equal to 1.7051 kilopascal, and we get also the value for P saturated at 25 degrees Celsius equal to Pg at 25 degrees Celsius equal to 3.169 kilopascal. Based on the equation for the omega for the specific humidity, where specific humidity equal to Cp multiplied by TWB minus TDB plus W saturated air multiplied by HFG at TWB divided by Hg at TDB minus HF at TWB. So the value of HFG at TWB we can determine by using the saturated water table, where the value of HFG also equal to the value of HFG at 15 degrees Celsius equal to 2465.91 kilopascal. 2465.91 kilojoule per kg. And the value of Hg at dry bulb temperature equal to Hg at 25 degrees Celsius equal to 2547.2 kilojoule per kg. And the value of HF at wet bulb temperature equal to HF at 15 degrees Celsius equal to 62.99 kilojoule per kg. And before we determine the value of omega, so we need to determine the value of omega during saturated air condition. Omega set equal to 0.622 multiplied by Pg at wet bulb temperature divided by P total minus Pg at wet bulb temperature, where Pg at wet bulb temperature equal to P saturated equal to Pg at 15 degrees Celsius equal to Pg at wet bulb temperature equal to P saturated at 15 degrees Celsius also equal to Pg at 15 degrees Celsius equal to 1.7051 kilopascal. And substitute the value that we obtain for omega saturated air condition. So we will get the value of omega saturated air condition equal to 0.01065 kilogram H2O divided kilogram dry air. And then substitute all the value into the equation of omega. So we'll get omega equal to 0.00653 kilogram H2O divided by kilogram dry air. Equation B, we need to determine the relative humidity, psi. So data given as shown in the slide for dry bulb temperature, wet bulb temperature, P total and also Cp value. Omega set specific humidity at saturated air we already determined from previous slide, equal to 0.01065 kilogram H2O divided kilogram dry air, and the omega, the specific humidity for the air that we obtain, equal to 0.00653 kilogram H2O divided by kilogram dry air. And P saturated at 15 degrees Celsius equal to PG at 15 degrees Celsius equal to 1.7051 kilopascal, and P saturated at 25 degrees Celsius equal to PG at 25 degrees Celsius equal to 3.169 kilopascal. So by referring to the equation for relative humidity that we obtain from the adiabatic saturation process, relative humidity psi equal to omega multiplied by PG at wet bulb temperature divided by 0.622 plus omega multiplied by PG at dry bulb temperature. Okay, so the value of PG at dry bulb temperature equal to P saturated at 25 degrees Celsius equal to PG at 25 degrees Celsius equal to 3.169 kilopascal. Substitute all the value that we have into the equation of relative humidity, so we will get relative humidity psi equal to 0.332 or 33.2%. Okay, the last question, we need to determine the enthalpy of the air, H value, where the enthalpy of the air will based on the dry bulb temperature, value, where H equal to HA at dry bulb temperature plus omega multiplied by HV at dry bulb temperature more or less equal to Cp multiplied by dry bulb temperature plus omega multiplied by Hg at dry bulb temperature. So Hg at dry bulb temperature equal to Hg at 25 equal to 2547.2 kJ per kg. Substitute all the value, so you get and also substitute the value of Cp and also the temperature for dry bulb into the equation for enthalpy. So finally we will get the value of enthalpy H equal to 41.8 kJ per kg dry air.